Thank you for being here to the IAPS seminar. Our today's speaker is Federico Esposito from the University of Bologna, where he works with Livia Vallini and Francesca Pozzi and Viviana Casasola. Federico is a PhD student at the last year. Actually, I think you are defending the thesis really in a couple of months, in a few months, let's say. And he's going to present us some very interesting results of modeling our galaxies to understand how the molecular component can help us to understand the environment of the AGN galaxies. This is a very interesting work, especially since mostly when we think about AGN, we think of high energy astrophysics. But however, nowadays we are still moving towards a new approach to astrophysics where multiple wavelengths are combined. And Federico's work tried to support with the millimeter and molecular gas component to study these environments. So we are very happy to have you here to present us your interpretation of these results. And the first is yours, Federico. And please, to everybody, mute yourself and keep your question for the end of the seminar. And you can write the question in the chat, or we will give you a possibility to talk at the end. Thank you very much. And the first is yours, Federico.
Thank you very much, Eugenio. And hello everyone for being here. So I'm Federico Esposito, I'm a PhD student from the University of Bologna. Okay, I will say.
No, we will put this model in the center, okay, and you stay here. Yeah, also because you need to change your slides.
Okay.
Okay.
Hopefully you can hear me.
Can give us feedback if you can hear him in the chat. Thank you very much.
Okay. So, thanks for the introduction, Eugenio. And yes, I will tell you about our work on modeling the molecular phase of the interstellar medium in AGN galaxy. And so first, I will start with an introduction of molecular clouds, then also a brief introduction about AGN. And then finally, I will tell you about our new model. So molecular gas in galaxies is made almost entirely of molecular hydrogen and helium also that doesn't like to be in molecules. Plus the most abundant and studied molecules are carbon monoxide or CO, then water, ammonia, and plenty more. And last but not least, there is also always dust mixed with the molecular gas. We know that it's pretty cold.
No, grazie, ma...
Sorry? No, okay. Is pretty cold thanks to the cooling of the CO lines, especially. And we also know that most of it is in giant molecular clouds or GMCs, and these are gravitationally bound structures. Thanks to its cold temperature and to its gravity, we know that GMCs can collapse and form stars. So since they are the star formation sites, this is the main reason for which we are very interested in the fate of the molecular gas. Okay, so how can we observe molecular gas? H2, molecular hydrogen, is the most abundant molecule, but unfortunately has no permanent dipole moment. So we can observe it, but only in a very special condition. While CO, or carbon monoxide, has a permanent dipole moment, which means that it has a rotational spectrum that we can observe mainly in the millimeter and sub-millimeter band. And the allowed transitions of the rotational spectrum are the ones with the delta J equal 1, where J is the quantum rotational number. And so the transition are called CO1 to 0, CO2 to 1, CO3 to 2, etc. When we put them together, we can study the CO spectral line energy distribution, or CO SLED. Here I plot the first 13 lines, which are the ones that are mostly studied. So they go from 2.6 millimeter to 200 microns as a wavelength. And in the local universe, we can observe the first 6 of this transition from the ground with single dishes as the Ariane 30 meter IAPS, or with interferometers as ALMA and NOEMA. While for the high J's, we can observe them only with airshell. Of course, the images from ALMA are the most spectacular ones. Here is an example of a nebula inside our galaxy, and on the right figure is a zoom in of that square, and in blue there is the CO322 emission, and it's astonishing to me to see how the complexity of the network that is between the substructures within the molecular gas. And one thing that I didn't say about the molecular gas is that it is turbulent. And I will come back to this because turbulence is in fact a key ingredient of our model. So when we zoom out and we see external galaxies, this is what we see. So these are again CO lines of nearby galaxies. All these galaxies have an AGN in the center. As we can see, the gas formed a spiral structure following the stellar spiral structure. So I will briefly introduce what AGN are and what is their effect on the molecular gas. So this is a good sketch of the central 100 parsec in logarithmic scale of a typical radio-quiet AGN. At the center, we have the supermassive black hole. Surrounding the supermassive black hole, we have the accretion disk, which is the main source of energy. The accretion disk emits mainly ultraviolet and optical photons, and then these photons are reprocessed by the surrounding gas. There are electrons in the hot corona, which Compton scatter these photons coming from the disk to X-ray wavelengths. And then there is dust in the polar region and in the torus, which absorb these photons and re-emit them in the infrared and sub-millimeter band. This is the effect mainly of radiation coming from the central source. But we also know that different kinds of pressure can give rise to winds and outflows, and then in different phases, which can then drag other gas in different phases and make also spectacular outflows. So I will give you 3 evidences of the so-called AGN feedback, which is the effect that this kind of small structure, which is just in the central 100 parsec, let's say, at most, of galaxies can influence the whole galaxy. So the first one is coming from our understanding of the universe on the large scale. If we adopt a cold dark matter universe, galaxy formation models tell us that the luminosity function of galaxies miss the observed luminosity function, and the theoretical luminosity function has some discrepancy at low and high luminosities. For the low luminosity, the main explanation is the so-called supernova feedback or stellar feedback in general that is missing in the main theory, and on the top end the AGN feedback. And in fact, new models can account for supernova and AGN feedback can fill these discrepancies. Then we have the very famous black hole mass sigma relation. So this is a correlation between the stellar velocity dispersion and the supermassive black hole mass over several orders of magnitude. So these give us clues that the black hole accretion has an effect on the surrounding galaxy. And this is also, we can appreciate it on cosmic times. So this is the star formation rate density and black hole accretion rate density over the cosmic time. And we can see that they peak at the same cosmic time around redshift 2. Since molecular gas is the fuel both for star formation and also for black hole accretion rate, for the black hole accretion, it is very important to establish how the AGN can influence and can have an impact on this phase of the gas. I split the AGN feedback in two different channels. One is the radiative feedback, and I'm mostly interested in the effect that X-rays coming from the AGN have on the molecular gas. And these create X-ray dominated regions, or XDR. And I will talk more about that. And then there is the mechanical feedback, which is the effect of outflows and shocks and jets, also in different phases that have on the molecular gas, which can make it outflow as well. And we study the radiative feedback mainly by analyzing the gas excitation, while for the mechanical feedback, we have to study the gas kinematics. For the rest of the talk, I will focus on radiative feedback because the model we developed is based on that. But if you're interested in mechanical feedback, we can have a chat later because I also got involved in a project on the mechanical feedback on molecular gas. So when talking about radiative feedback, we have to carefully differentiate between AGN and stellar feedback. Stellar feedback is mainly due to far ultraviolet photons coming from young stars, and these create photodissociation regions, or PDR, in the ISM. The far ultraviolet flux is mainly expressed in these G0 units, while the XDR is an analog but created by X-ray radiation coming from the AGN. Here is a sketch from a review by Wolfire, Vallini, and Chevans of 2022 of the structure of a PDR. So from the left, we have the far ultraviolet flux coming from young stars. And at the beginning of the PDR, we have the atomic layer, then a transition layer in which there is some molecular hydrogen, but the carbon, for example, is still in the atomic form. And then we have a fully molecular region deep into the cloud at the high visual extinction or column density. We can see that it gets pretty cold, and the main cooling lines are far infrared lines of carbon and oxygen for the atomic and transition region, and CO for the fully molecular region. From the same review, we also have a sketch of the structure of an XDR. Again, from the left, we have the incident flux. In this case, it's X-rays. And then we have, again, an atomic and molecular regions. For the fully molecular regions, the CO rotational lines, so the lines of the CO sled, are the major cooling mechanism. And the X-rays can penetrate deeper into the cloud. We have a factor of 10 in column density more, and also in radius.
So what is the density you're for your?
So here, well, this is a very schematic sketch for general XDR, but later I will talk about density. Oh, for example, also already they appear in this plot. This is from Pensabene et al. 2021, and they made this plot using Cloudy, which is a radiative transfer code that can simulate the effect of X-rays and ultraviolet radiation in the gas. And by dividing it in zones and studying the physics and chemistry in every zone due to the radiative transfer, basically. Here on the left and on the right, we have PDR and XDR CO sleds. And the gas density of the models here are the first and the second panel are 10 to the 3 and 10 to the 5 centimeters to the -3. And again, for the XDR, they are the same. What we can see is also the variation of the CO sled due to the different incident fluxes that is given from the different color opacity. And we can see that XDR especially is very important to take into account the different X-ray fluxes because it can vary a lot. Okay, so at the beginning of my PhD, we tried to study the effect of the AGN on the molecular gas. especially when compared to stellar feedback, from observations only. So what we try to do is we gathered a new AGN sample. We selected by going into the Herschel results because we needed the full CO SLED sample that lists the CO 13 to 12. And then we selected only the galaxies with intrinsic X-ray luminosity over 10 to the 42 to ensure that they were AGN. We also collected 70 micron images, again from Herschel. And then, if available, we also collected ALMA CO65 maps. This work has been already published by MRAS in 2022, and I will briefly introduce it. So the sample in the end resulted in 35 galaxies, all local. Maximum redshift was 0.15, and here are some optical images of them. So at first, we gather all the informations to try to compare the AGN sample with non-AGN on the Schmidt chemical plane. So first, we use these relations found by Viviana Casasola from the dust media sample. That is a radial profile for the CO emission in nearby galaxies. And then we calculated the molecular mass from the CO1 to 0 emission by adopting CO2 to H2 conversion factor, which is this alpha CO. We adopt a galactic, a Milky Way CO to H2 factor to calculate the molecular mass, mainly to compare with other samples. Then we calculate the star formation rate from the 70 micron images we collected from the Herschel images. And then we calculated the surface density of molecular mass and star formation rate within the same radii. And these are the results. So the blue points are AGN. Our sample is the star symbols, but there are also other samples from the paper by Lambert et al. 2020. And we compare them with non-AGN, which are the gray points. And what we could see is that the two samples, the AGN and non-AGN, cover more or less the same parameter space, and there is no change in the inclination, in the slope of this relation. So our conclusion was that the AGN effect was not evident from this plot. This may be due to the fact that these quantities are calculated over a kiloparsec scale, so it can be that the AGN effect is too diluted. Or it can be because we are tracing the molecular gas only from the CO1 to 0. And probably we have to go to higher frequencies to see it. So what we did was to counteract the fact of the dilution effect, to try to zoom in to the galactic centers. But from Herschel observation, which are the ones from which we have the CO SLED, the beam is very large. Here you can see the NGC34, which is one galaxy of our sample, optical image, and the CO625 beam from SPIRE is very large. So for the galaxies that were available in the ALMA archive, we went for the CO625 images traced by ALMA. And we saw that for a subsample of the galaxies, this was concentrated in the central 500 parsec of diameter. So we focused on this diameter of 250 parsec of radius, and we assumed that all the lines from the CO6 to 5 to the CO 13 to 12 were confined at least within this radius. So we computed the far ultraviolet and X-ray fluxes within this radius, and we tried to compare CO line ratios with the observed far ultraviolet and X-ray fluxes in our galaxies. This is because from the literature, we know from previous radiative transfer models, we know that the XDR component of the CO SLED is mainly concentrated in the high J region of the CO SLED. So these are three works that use the single galaxies and try to fit the CO SLED with PDR and XDR models. And XDR is always the component that can fit the high J part, let's say from CO6 to 5 going upwards. These models are the kind of simple models. They assume every curve assume a single gas density and a single incident flux. And I will come back later on this because our new model is trying to improve these simple models. So our results for this sample of AGN is this. Here we have the CO line ratios of different lines of CO9 to 8, CO 11 to 10, CO 13 to 12. We were just trying to explore, let's say, the high J part of the CO slab, divided by the CO6 to 5, because we knew that CO6 to 5 was coming from 250 parsec of radius. So we compared these line ratios with the far ultraviolet on the left panels and the X-ray fluxes on the right panels at this radii. What we found here, every little square is a galaxy of our sample. The blue ones are detection, while the red ones are upper limits. And what we could see is that we tried to fit regression lines, and we found only sublinear relations between these quantities. So our conclusion was that neither PDR nor XDR heating are dominating these observed line ratios. We also tried to.
Can I?
Yes, absolutely.
No, if I understand it correct, so between the line that is written on the title
Yes.
and did you take into consideration different schema of each observation?
No, actually, well, what we did was to check on the ALMA archive the available CO6 to 5 observation, because from ALMA we cannot observe these lines.
Yeah.
They are too high frequency. So from the CO6 to 5, we know that for all the galaxies of our sample, which are pretty close, the emission is within the beam, is within the actual beam. So, and the same applies also for the other lines.
These lines are resolved, no?
Yes.
You cannot, you cannot estimate the emitting size from the alpha image.
From the CO6 to 5, yes.
Yeah.
Yes. That's where this 250 parsec of radius comes. Basically, that's the median.
You are assuming that this higher CO line is coming from a region of 250 parsec.
Yes.
So
At most.
Yeah.
They can come from a smaller region.
Okay.
But the C25 comes in principle also from other regions of the galaxy, which is lower excitation, and it's also excited by PDR conditions, which are all over the place on the disks, right?
Yes, in principle, yes. But what we saw for these galaxies, I mean, we have like 7 or 8 of our sample that is on the ALMA archive for the CO65, was that on average was coming from the center of 500 parts. Of course, there were also larger emissions from some sources, but we took this as an average among the sample. So we also try to compare these results with some models made with Cloudy, and these are the results. Mainly, these are the same plots of before, but I overplotted these colored lines, which are Cloudy models at fixed gas densities, which is the color of the line. Going from yellow is 10 to the 2 to the purple lines is 10 to the 6 centimeters to the -3 at different far ultraviolet or X-ray fluxes, which is on the x-axis. And what we could see is that the observed line ratios can be reproduced by PDR models only by assuming very high density. So between 10 to the 5 and 10 to the 6 centimeters to the -3, while for XDR models, we can reproduce them also with lower gas density. So this was our work from 2022, and from this we started to develop our new model mainly based on the work that Livia did in 2017, 18, and 19, starting also from cloudy PDR and XDR models. Basically, we wanted to exploit also all the observations that we collected for this sample of AGN. So for every galaxy, we have an estimate of the molecular mass radial profile, of the far ultraviolet flux, and of the X-ray fluxes from the AGN position to the external periphery. And so our idea was we wanted to start our modeling from single giant molecular clouds. And then we wanted to basically fill a galaxy volume with molecular clouds following the molecular mass radial profile. So we know that within giant molecular clouds, there are overdensities, and these overdensities follow a turbulence-driven probability distribution function, which is with this log normal form. And so we generated some synthetic giant molecular clouds from 4 parameters. So the mass, the radius, the mean density, and the Mach number. And then we can generate the probability distribution function of the clumps, and we can extract clumps from this distribution to fill the GMC mass. Then we use Cloudy to compute the radiative transfer within every single clump, and by summing all the clumps, we can have the CO-SLED of a giant molecular cloud. This is an example for a GMC we generated. So in the left is PDR models, and on the right XDR. So basically, this is the effect of stellar and AGN radiation on this molecular cloud, which is composed of several clumps, and I bind the clumps by their density, and these are the colored lines, while the dashed black line is the whole GMC, and the gray shading is for different incident fluxes. And as you can see again, on XDR models, the incident flux can make the CO-SLED, the final CO-SLED vary a lot compared to PDR models. And this is already in solar luminosity units, as you can see, because mainly we could compute the volume of the single clumps and of the GMC, so we could integrate the flux into solar luminosities. Then we generated different GMCs, and to represent more realistically single galaxies, we distribute them with a power law in mass, and we follow some works, especially based on the Milky Way. And so what we did, we generated 15 different GMCs. We distribute them with this power law. And then we use the observed radial profile to fill the molecular mass radial profile, and then we match every GMC based on their position with an incident X-ray or far ultraviolet flux.
There is a mass segregation in the way we distribute the molecular clouds as a function of the galactocentric radii. More massive.
No, in that sense, no. Okay. We didn't. No, it's we just
uniform in mass.
Exactly. At every radius, you can find
mass function.
Exactly. So these are the results for galaxies. The black line with the arrow bars is the observed CO-SLED, and the orange line is what we call the baseline model. So this is just the CO-SLED that comes from our modeling without any fit involved, and it is already in solar luminosities. So it doesn't match perfectly the observed CO-SLED, but these initial results were very promising, because to make these baseline models, so these orange lines, the code doesn't know at all the observed CO sled, just know the molecular mass of the galaxy, the far ultraviolet and X-ray fluxes. And
from a global galactic viewpoint.
yes, yes. Well, we built the radial profile. For the far ultraviolet, we use the air shell images from the infrared, and we convert the infrared to far ultraviolet, basically, by assuming that the infrared emission is actually far ultraviolet emission from stars reprocessed by dust in the infrared at 70 micron. And for the X-ray, we take the intrinsic X-ray luminosity coming from the center, and then we just divide it by 4 pi r squared. We also input an attenuating column density to attenuate the X-rays. And then for the molecular mass, we use the optical radius, because from the works by Viviana, we know that the molecular gas follow a radial profile that is based on a scale radius, which is a fraction of the optical radius. So we use all these informations to make these orange curves. But of course, they don't work perfectly. So here I also plot for these two galaxies the PDR and XDR components of these curves. In some cases, for example, in the first case, there is clearly a problem of normalization from the observed to our model CO sled. And so since of course we fill the galaxy based on the molecular mass, which is based on the CO120 emission, we adopt at the beginning a fixed alpha CO, a fixed CO to H2 conversion factor for every galaxy, but of course this cannot be a universal conversion factor for the galaxy. So we thought about.
In this prospect, can you use your model to infer information on the map?
The molecular mass. Well, actually, it's the other way around. We use the molecular mass as a pattern.
You can, once you more or less at this paper, your principle can.
Yes, this is an implementation that we want to make, but it's still not ready. But yes, in principle, in the next future, we would like to include that.
The galaxies of your sample are all, do you have any independent indication, but from optical spectra, for example, of the metallicities that could drive the different alpha CO for the different ones?
We didn't check that. I mean, not for sure, there is not for every one of these galaxies. For some, yes, there are some papers that try to study, but especially the CO conversion factor, even radially dependent, because since it should depend on metallicity, and metallicity may vary with radius. But no, we didn't check the values that we will find, because I didn't say it yet. But basically, what we wanted to do at this point is to treat this alpha CO as a free parameter. To fit the observed CO sled starting from our baseline to match. The other free parameter instead is the gas column density, and this is only affecting the XDR component of our model. This is because the column density, we use it to obscure the X-rays that are coming only from the AGN, while the far ultraviolet photons, of course, are coming from stellar populations all around the galaxy. So the result, and so we treat these two as free parameters, and we apply Markov chain Monte Carlo model to find the posterior distributions of these two parameters. And our results are these for these galaxies. So I overplot now the best fit CO sled, and as a bonus, of course, we can infer for these galaxies the alpha CO and the gas column density. And so these are our results. For the alpha CO is the histogram on the left, and for the column density is the histogram on the right. For alpha CO, we are recovering reasonable values from our models. Some of them are consistent with galactic values, which is the dashed line. Some other are consistent with Starbucks galaxies. And for the column density, we are finding low values in general. So very close to 10 to the 22 centimeters to the -2, which is for us the lowest value. Basically, for column density is lower than 10 to the 22 are not obscuring enough the AGN, so we are not considering that.
So you were putting in your baseline model, you were putting more material because you had a very depressed XDR emission.
Yes, in this case, yes. For example, yes. In the case of NGC 5135, yes, we were putting more column density, which is well, it's very small, but you can see that we were putting a median column density of 10 to the 23.4,
which is too much.
Which is too much for this galaxy, exactly. So these results have been already submitted to NRAS, so hopefully they will be soon available on the archive. And another important result that we found is that the XDR component of these galaxies is very luminous already from the CO43 or from the CO54. So the percentage of the total luminosity emitted by the CO is dominantly made from the XDR component for the IJ, but even for the mid-J transitions, which is, I mean, I'm not saying that the PDR models are not emitting these lines, but not enough to explain the observed CO SLED. Of course, we are starting from CO SLED that are pretty flattening over the mid-J and IJ because they are from AGN galaxy. So these results, of course, apply for AGN galaxy. Another thing that we could derive from our model is the size of the emission from all the different lines. So here again, there are the 13 CO lines on the x-axis. On the y-axis is the radius from within we produce 90% of the luminosity of a given line. And the several lines are the different galaxies of our sample, and we color them with increasing X-ray flux taken at this scale radius RCO, because we found that actually the main reason between the difference among them is exactly this X-ray flux. So a low X-ray flux will result in a smaller XDR region, which is the one that is emitting the high J lines. While for a high X-ray flux, this XDR will grow and be as large as the low J.
But here, for all of these, you are using a single value of hydrogen, of obscuring hydrogen column density, because the X-ray flux, maybe it's a combination between the size of the XDR and the amount of obscuring material. So
yes, in this case, the column density is a single value within a galaxy. It's different for every galaxy because these are the values that we find, this histogram. But yes, within the galaxies are single values. At the beginning, we were using a radial profile, actually, which was basically the integration of the molecular mass to calculate the column density. But when we decided to treat it as a free parameter, we decided to use it as a single value to not complicate too much the model. And so, yes, these X-ray fluxes are obscured by a single value of column density, which is the median average value of obscuration, let's say, within this galaxy. And this model is already available online. We call it Galaxy SLED. You can find it on GitHub. You can download it. There is a Jupyter notebook that show you how it works. And hopefully the paper will be soon available on the archive. And so these are my conclusion. This is the model in a nutshell. So we built this physically motivated model starting from the internal structure of giant molecular clouds, which are made of clumps with a distribution which is induced by turbulence. We applied radiative transfer models, PDR and XDR, on the single clouds and the full GMCs, and then we distribute them following a mass distribution and following the observed radial mass, molecular mass radial profile of our sample. and we could infer this alpha CO and column density for our galaxies. We found that AGN feedback is dominant for lines from the CO43 going upwards. And given the observed galactic properties, we can predict the intensity and physical size of the CO lines. That's it. I'm taking.
Thank you, Federico. So, if there was some discussion already during the talk. So, if there are more questions, I will also give I will favor a question from people online first, and then I will go to Milena that already has raised her hand, and also Sergio. So, any question from people online? Okay, I don't see any question from people online. So, Milena, you have a question?
Yes, the fact that the slide where you show how you populate your the
Like this.
The population now.
This one.
Yeah, no, this one. Okay.
This one.
So yes.
Okay.
So you use the Roman 2010 for the distribution of masses. Okay, I'm wondering what is the range of masses that you allow, because this power law is actually extracted for a high mass.
Yes, you're right. I forgot to tell you this. So we generated the GMCs within 10 to the 4 and 10 to the 6 solar masses. But yes, the relation was extrapolated only from 10 to the 5, if I remember correctly, to 10 to the 6. So we are basically extrapolating it to 10 to the 4. We also tried the differential power law index, assuming that there was a single
power law index is from 1.6 to 1.8. I don't think that it is. What I think that you are over populating the low mass end of the distribution, because we don't see this kind of the power law. You know that around between the 7 to the 4 to the 5, we have a flattening of the distribution.
Okay. Well, this is something I would love to discuss with you, because I think you know better than me what is the actual distribution of molecular cloud. So we assumed a simple power law because was the simplest choice, and also following this work, but also other works, also based on nearby galaxies. But yeah, of course, the lowest values, I guess they are also hard to observe because they are kind of small. We are talking about like 50% of radius. So.
But I think the main question is to understand where most of the mass is inside the molecular cloud that are 10 to the 4 solar masses in total, or on a higher, because in the end your luminosity will depend on where is most of the mass.
Yes. And
since this is if I understand correctly, this is a linear scale in the y-axis. So
yes.
I would say that then you need a lot of 10 to the 4 solar masses to produce enough. Anyway, 1 second, Sergio, there is a question from people online. And the question is it possible to use the galaxies LED model on galaxies that do not host AGN?
Well, not as it is implemented now, because it needs an X-ray flux. But yeah, I would like to expand it. I mean, it will be a kind of easy fix. It's just excluding all a part of
the contribution section.
Yes, we're taking into account only that. Yeah. It doesn't work now in that sense, but it can.
The question was from Mary Polletta,
okay,
and
thanks,
I think that the speaker answered your question. If you you can write on chat if you have more question. Anyway, Sergio, you have the question. Go.
Yes, can you go back to the one of the previous slides where you showed the relationship between the density of star formation rate versus column density? This one, yeah.
Yes.
You didn't. I mean, you said that there is no difference, but if I was a cosmologist and I start seeing things, I would see that the blue points are all on the lower, let's say, side with respect to the non-AGN. So I don't know. One can say something about possible feedback that is quenching star formation or something like that.
Yeah, this is something.
You chose to say nothing on that
No,
side.
exactly. I just say nothing because we didn't explore that that possibility actually. But this is yes, this is an interesting. This would be an interesting development. Let's say to explore more these on larger samples or to see if yes, if there is an effect on the high end of this diagram that suppress the subformation and molecular gas. But yeah.
I was about to make this exactly the same question. It's clear that only fit the rate of
These are not actually or they are just fixed the depletion time line. So
over the yes.
Can you go back to the distribution of clouds?
yes.
That is within a given one molecular cloud. So the question is, what is the observational counterpart of this? You said it's a model, but I guess the observational indication on the cloudiness factor and also the density of your single cloud. I recall, for example, that there's some evidence of very high dense clouds in this so-called window after 10 to 8 to the 9. And the related question is how do you take into account the relative transfer of this such a spread of densities? And if you also have some, indication of connection between the optical lines, because at such density you can expect to have oxygen or metal lines in the optical spectrum that can give you some indication of the density of your lamps.
Okay, I will try to answer you. So for the observational counterpart, now I don't have the name because these two are for sure both theoretical papers, both Vasquez, Seminari, and Federer and Klessen. But I can find them. I have them in my computer, but I don't have on top of my tongue. While for the radiative transfer, yes, we use a grid in incident fluxes and in gas density, and then the grid was with spacing between different values of gas densities, the order of 0.25 in logarithmic scale, and then we interpolated between the values. So we computed basically the radiative transfer. Well, not for every cloud because there are thousands, but for many of them, and then interpolated between the values to find exactly the solution for every single cloud. While
The optical
lines.
Because I'm expecting to get excitation.
Also,
organize the line.
Okay, you were also naming about you were saying about the 10 to the 8 or 10 to the 9 centimeters to the minus 2 to the minus 3 gas density, and honestly, I don't know for such high
which areas, for which region.
Yeah, this is my question. So it is also the
size of the
size and stuff. Is the let's say the covering fraction of the volume fraction of
the volume fraction is low, is below 0.5, below 50% now. I think around 30%, but for sure less than 50 of the GMCs. And as for the size, is they range, but subparsec for sure. I can give you the exact numbers. No, I don't remember that. The GMCs are going from 3 to 30 parsecs, something like that, and the clamps, of course. are smaller than that, so fast I can. And for the optical lines also, I'm not an expert on optical lines emission, but you mean like recombination line, like
You can have both recombination and also excitation lines of the field and two, the field shocks there.
At the end, you find these lines, right?
Yeah, but we also have in start forming the clamps. I mean, it's not only
I
X-ray
agree.
and yeah, of course.
yeah.
So you have also these diagnostics from
That's
about with
Yes,
the line diagnostic that it would be interesting to
Yeah,
use the
I think it's
the handle on the physical conditions that you're
We didn't look with it. Thanks. This is an interesting idea, and we didn't thought about it, but yes, that's a nice development.
So if there are any other questions?
Just one final little thing, because you implicitly said that in your last slides that the size match the size that you derive, but with your best fitting matches the observed X-ray. So implicitly you must have compared. I mean, once you fit with the varying the column density,
You are talking about this one.
this thing here,
Okay.
yes. I mean, you value the alpha CO and you value the total column density essentially. But then I suppose that since you're talking about XTR, there must be X-ray observations by which that predicts you can predict an amount of X-ray flux coming out of this,
Yes, yes.
and this matches the observed values.
Well,
When you with your best fit of alpha and column density of hydrogen, that would best fit your CO's level, also fit the amount of X-ray that you actually see from these galaxies.
Well, we only see the luminosity from the AGN in its space. So we started from that. Not the observed value, but the people that work with X-rays from the AGN give an intrinsic values of the AGN luminosity in X-rays. So between 2 and 10 kiloelectron-volt for X-line observations, but also from new star observations. And we started from that, which is a single luminosity value that is coming from the exact center of the galaxy. And then we calculate the flux, just dividing the luminosity by 4 pi r squared, and also by column density. And in this way, we can calculate the X-ray flux at every radius, but we don't have this information. So I was saying here, I was naming the XDRs because we know that it's the XDR component that is the footprint of those IJ lines, and those are the lines whose radii are varying a lot among the samples. While for the low J lines, the variation among the sample is minimum, but for the IJ lines, they are varying over an order of magnitude. So when I discovered this, I tried to understand why it was so, and I found out that it's actually well correlated with the X-ray flux at a certain radius. Here I took this RCO just to select a single radius for every galaxy, and then I divided also this observed R90% into this RCO, which is different for every galaxy, and is 20% of the optical size. So yes, this is an XDR effect, the effect of X-rays, basically. When there are a lot of X-rays, or there is a powerful flux of X-rays, we can see these lines originating even from kilopascal scale. While for low X-ray fluxes, which can be a low power AGN or even a high power AGN, but attenuated by a lot of gas, the XDR shrinks to 10% of what we're thinking.
I have just one question before leaving, because we also have to leave, and there are other people requiring in the room. My question would be mostly about you show all the CO's ladder, right, with all the CO, but in the end we have this kind of observation only for some sample of objects, and why it's very powerful as the entire information. If you need just 1 or 2 indicator of which which line would be very interesting to probe for your model. I mean, what I mean is that you use your model to calibrate with the entire CO splatter, but in future you want to observe other AGN, and what will be the lines that we would like to observe to really pinpoint the XDR contribution in PDR. For PDR, I understand it's the low J, but XDR
is the IJ. So I would say that if you need to select 2 or 3 lines, I will do it with a low J, a mid J, and a high J line. And in this way, you can already put 3 points on this curve.
Yeah, because
or at least 2, but the more distant they are, the better it is.
Yeah, because I think that the one that are in the
It's like after, no, where you should be contributor, what is the interest? No, where I should you, yes, indeed, XDR plays the IJ, but you see, we have
Significantly contribute
also in
Yes.
the other, so if you use a model that considers both, I think also with the, so what we can observe from ground, you can.
I think this is I mean, this is very interesting in the sense that tells you that for the IJ, you need you need the IJ for to the XDR contribution. But in the end, you notice that the slope of the sled sometimes is decreasing, sometimes it's flat. So this is flat, you just need 1 point or 2. And if it's decreasing, that tells you some other information. And since the mid J are observable from ground with ALMA, also at high spatial resolution, that would be, I mean, it would be interesting, but in future, you really need to go to the high J, what kind of information give you? So we are thinking another infrared observation of the sky.
Yes, the fact is that we don't have,
Yes.
Yeah, but
we don't have
Not
that.
yet.
Not yet. And not in the local universe. I mean, at high redshift, of course, you can start observing also with ALMA or other ground-based telescopes. Even
If these X-ray people let us launch a small infrared satellite, it would be very great. I would say,
absolutely, I would love that.
no, but there is now the probe, the exoplanet planet people would be there.
anyway, very, very interesting. So I think that we can close here and thank the speaker. And see you next time for the IAPS seminar.